Hello, my name is Armin Tavakoli, and I'm a postdoc at ICOCI Vienna in Austria, here to give a talk at the Quantum Physics and Logic Conference in Gdansk for this year. The title of this talk is a semi-device-independent framework based on restricted distrust in prepare and measure experiments. Generally, this talk concerns the question of certifying quantum devices and quantum correlations. Indeed, quantum correlations are at the heart of the many advantages and abilities that quantum theory provides in order to beat the limits of classical physics and classical predictions. However, the central question is under which assumptions we want to certify these quantum phenomena or these quantum advantages. The semi-device-independent framework that I propose here is one among many already established avenues in which to approach this question. So before arriving at this proposal, I would like to review some of the basic lines of research to answer these types of questions. Here, I will take a look at the standard picture, which is taught in every textbook on quantum information, the device-independent picture, and also the semi-device-independent picture, which is the focus of this talk. Indeed, these provide three different routes to the certification of quantum correlations and quantum devices. In the standard picture, one typically makes the rather generous assumption that lab operations can be flawlessly controlled. When we implement a measurement in the lab, we truly are perfectly doing it, and so on. This captures many typical quantum information tasks. For example, in an entanglement witness, measurements in the lab are assumed to be perfectly controlled. And another example, in the BB84 protocol, stipulates that one needs to prepare certain states and certain measurements from which to extract a shared quantum key. In a completely opposite picture, the device-independent one takes the view that actually our laboratory devices are black boxes about which we know nothing. At best, maybe that they're operated by quantum theory. So here, one adopts the view that we can only make deductions based on the statistics that these black boxes develop. So in a sense, it's the completely opposite of the standard picture. But the semi-device-independent one is something that is less colorful. Neither does it assume flawless control, neither does it assume that we have no control at all. Instead, it aims for something in between. In the semi-device-independent spirit, one wants to make a compromise between the standard approach and the device-independent approach to have something that is useful for practical considerations. Of course, the standard picture and the device-independent picture both come with certain advantages and drawbacks. One is that in the standard picture, you are vulnerable to small imperfections for the fact that laboratory devices never are perfectly controlled. But the advantage is, of course, that with these assumptions, it's relatively easy to implement these protocols. For a device-independent picture, it's the opposite. The black box assumptions mean that you are very robust to imprecision and even to general attacks for malicious parties. But the price to pay is that these protocols are hard to implement. The semi-device-independent picture aims to harvest the advantages of both of these. That is, by making only a small and reasonable assumption, we aim to protect the protocol against imperfection and even attacks. But at the same time, we don't necessarily involve entanglement nor very heavy assumptions, and then can comparatively easily implement them in laboratories. The typical framework for the semi-device-independent approach to quantum information protocols is the prepare and measure scenario. In this scenario, there is a sender called Alice and a receiver called Bob. Alice takes some classical input X, sends a message to Bob. He takes classical input Y and produces an output B. The main idea of semi-device independence is to analyze the correlations of outcome B given message X and measurement Y, and understand how these correlations can behave in quantum mechanics. Once one understands the predictions of quantum theory, one can then harvest these for quantum information applications. But naturally, when one wants to take a compromise route between device independence and standard picture, there are many different options to choose from, and indeed many have already been considered. It's natural to see that in a prepare and measure scenario, if one wants to make any interesting statements, one must introduce some form of assumption. To see this, one can note that if there is no assumption, Alice can always send X to Bob over the channel, and Bob can then produce any distribution he likes, regardless of the physics of the theory that operates the system. So one reasonable and useful assumption needs to be introduced. And these are some of the avenues that have already been considered. For instance, the most popular and well-studied framework is to assume that the message of Alice has a dimensional limit, but can otherwise be uncharacterized. Another more recent approach is to take an information route and say that the dimension can be unconstrained, but the amount of information Alice sends to Bob over the channel has to be quantitatively limited. This is a weaker assumption than dimension. A perfectly different way is to say that Alice has two messages, but we limit the overlap between them so as to prevent them from being perfectly orthogonal and then perfectly distinguishable to Bob. Yet another approach is to take an energy limit and say that the energy with respect to some operator in the ensemble of messages sent by Alice has to obey some sort of limitation. Indeed, some of these assumptions, in particular the dimensional bound, has some substantial drawbacks. One is that dimension typically isn't an observable. We can't measure it in the lab, even if we had perfect devices. Another issue is that the dimension typically fluctuates from round to round, and it's not something we can certify in every given round of a protocol. In contrast, the energy bound can resolve this problem by, for instance, considering how much energy we transmit on average. Here, when I propose a distrust-based framework for semi-device-independent quantum information protocols, I aim to harvest advantages from all of these different frameworks to propose something that is operationally useful. So in the distrust-based framework that I present here, the goal is for Alice to prepare certain states, which we call psi-x, and take them to be pure. But realistically, we understand that these are not the states that Alice will prepare in her lab. Those lab states we actually call rho-x, and these can be mixed. They are actually what is sent over the channel to Bob. About Bob, we make no assumptions at all. And indeed, the dimension of the state that is sent is not restricted either. Now, the distrust-bounded approach is to say that there is a limit between how inaccurately our lab state represents our target state. That is a bounded distrust. Distrust is something we quantify through the fidelity between the two states, which here boils down to simply the transition probability. We say that there is a limit on the fidelity between the lab state and the target state, which is bounded by the distrust parameter that we call epsilon x. If epsilon is 0, the two states are perfectly equal. If epsilon gets larger, then the lab state can be further and further away from the target state that we consider. Importantly, deciding or estimating the distrust in a given state can be done simply by a measurement. It is operationally meaningful. That is, we need only to measure the overlap of the lab state with the state that we were targeting. So the procedure is very much simple. We decide the states that we want to prepare, we estimate the distrust in the states that we actually did prepare, and then we make deductions about the correlations that we see. Needless to say, the more distrust we have, the more general can the set of correlations be. How much distrust is then meaningful to have? Naturally, if we have no distrust, we know very well how to operate the system. But how much distrust can we have before everything is trivialized in the sense that we can no longer see any form of quantum correlations? A simple limit can actually be found. We imagine that Alice prepares n different states. Then take the extreme case in which all the target states are identical. That is, every state Alice prepares is simply supposed to be the zero case. Then we may imagine that actually the lab states are the quantum Fourier transform of the computational basis. That is simply the Fourier basis of d-dimensional or n-dimensional Hilbert space. So the fidelity between the target state, 0, and this Fourier basis is simply 1 over n. Meaning that if we so wished, at the distrust of almost 1 as n becomes large, we could send the full information to Bob. This means that above this limit, it's no longer possible to witness any form of physically interesting correlations. But below it, it is very much possible to distinguish quantum theory from more general theories, such as, for example, classical models. So let's take a look at how we can understand the set of quantum correlations. So here, this is illustrated as this convex set here in gray. This is the quantum correlation set when you have fixed the target states and the amount of distrust that you want to allow. And for simplicity, we look at some task function, that is some linear function of the probabilities that we, for sake of simplicity, want to maximize. So indeed, when we are given a task function, our job is to try to find this point here where it crosses out of the quantum set. For this purpose, we have two general methods. One is interior point search, and the other is exterior point search. What the former does is that it takes a task function and the target states and the distrust, and it tries to find the largest value of the task function from inside the quantum set. This, in general, provides lower bounds on the optimal quantum correlations possible, but it can be efficiently applied to essentially any problem. This is complemented by the exterior point method, which is based on semi-definite relaxation hierarchies that I won't go into detail here. But in spirit, its task is to give an outer approximation to the quantum set. By doing increasingly fine hierarchies of the quantum set, one can approach the quantum set or the optimal point and hopefully make the lower and upper bounds match. In this sense, this tool that we develop applies to characterize the set of quantum correlations from the inside and the outside. As a simple example of how distrust can affect the simple quantum protocol, we can look at quantum state discrimination, which is simple enough to admit an analytical solution that doesn't even need these two methods that I've just mentioned. In state discrimination, Alice has two settings, and Bob is trying to guess which one she had. The two states can be taken to be pure, for example, in the disk of the Bloch sphere with an angle theta. Usually, when the states are perfectly known a priori, the optimal winning probability of distinguishing these states is given by the Hellstrom bound, which is given by this expression here. This is a result long known since several decades. But what happens when we don't assume that Alice perfectly prepares the states that she was supposed to? Indeed, what happens if we allow for a distrust of epsilon in each and every state? It turns out that what happens is entirely intuitive. We keep the Hellstrom bound, but in addition, we have to allow for a perturbation, a distrust-based perturbation that looks like this. As we increase epsilon, this perturbation gets larger, and it also depends on the states that we were actually targeting. In essence, if you allow for more distrust, you get the same correlations as in the standard picture, plus an even stronger term that can further boost your winning probabilities. Let's take a look at the more concrete application. That is one of trying to distinguish quantum from classical measurements. A quantum measurement is, of course, a positive operator valued measure, which goes into the Born rule here in the form of this capital E, which represents measurement number Y and outcome number B. What I call a classical measurement is essentially a quantum measurement with a post-processing. That is, the correlations that Bob observes for his different settings Y are actually based on him performing a single measurement, which in the basis that I call EK, and then post-processing this, the outcome of that measurement, together with his input into the final output. So can we distinguish a quantum measurement from a quantum measurement with post-processing? Well, for this, we need at least two measurements, so state discrimination isn't good enough. So for this purpose, we go to a slightly more complicated settings in which Alice has 3 inputs and Bob has 2 different measurements with binary outcomes. And then we pick a task function, this linear witness of the correlations, which looks like this. So here E denotes expectation value, first index denotes Alice's setting, and second index denotes Bob's setting. So in a quantum picture, we get something like this. This is obtained using the STP relaxation method for exterior characterization of the quantum set. So on the x-axis here, we have the amount of distrust, and on the y-axis, we have our task function. In blue, we have the quantum result, and in red, we have the classical one. So we see that at a perfect trust, then of course there is a substantial quantum advantage. But this starts to wash out as we increase the amount of distrust. Already at about 3% distrust, one can simulate classically the ideal quantum protocol. And indeed, these two converge, and eventually the quantum advantage is washed out. So indeed, up to realistic but not too large amount of distrust, one can certify that the operation of Bob is truly quantum. Another application that is worth mentioning is random number generation. So here we take the same protocol as before, but now we want to certify that the outcome of Bob for some specific setting of Alice and Bob can be considered a quantum random number generator in face of some external eavesdropper. To just quickly give an overview of what type of results one can get for this, we have here randomness on the y-axis, and on the x-axis we have the amount of distrust. Here, for the different lines, blue, red, and purple, we have an optimal implementation in which we generously assume that we observe the theoretically maximal correlations. Here at 99%, we assume that we have small amounts of error in our implementation, and here that we have even a bit more amount of error, 3%. And then one sees that how the randomness rate drops off with the amount of distrust that we introduce in the system. Essentially, the less you trust the system, the more powerful are simulations of an eavesdropper that try to emulate your correlations, and therefore the less amount of randomness you have, and the faster it dies out. But indeed, we see already here that at experimentally realistic amounts of distrust, as say 1 or 2%, one can obtain a substantial amount of randomness. But it also highlights the fragility of quantum protocols to even small amounts of error that may occur quite naturally in realization. So in conclusion, what we introduce here is a distrust-based framework for semi-device-independent quantum information processing focused on prepare and measure experiments. This does not make any assumption on the dimension, but it's instead based on a notion of distrust, which is equivalent to fidelity, that can be operationally useful in the sense that it can be measured in a laboratory and independently asserted for the different preparations that one might be interested in. So natural problems for this avenue is to try to understand its applications, for example, in more efficient random number generation or in real-life QKD applications. But also on the fundamental side, I find it particularly interesting to ask how little trust is actually needed for quantum correlations to admit a classical model, but also to take the opposite view and ask how much distrust is needed for established quantum information protocols to no longer be useful in cases where we already assume quite strong constraints. So with that, I thank you for your attention.